Welcome to the Explainer. So let's jump right into some massive AI news today. We are looking at what might honestly be a fundamental shift in the AI world. OpenAI and Broadcom just released engineering samples of a brand new custom processor named Jalapeño. Now, this isn't just your standard product update. This is OpenAI officially making the leap from purely software into physical silicon design. It's a platform designed specifically for large language model inference workloads, and let me tell you, it has some absolutely massive implications for the future of AI infrastructure. Here is our roadmap for today's deep dive. First, we'll meet the Jalapeño chip. Then we'll ask why build custom silicon in the first place. After that, we'll break down inference versus training, take a look under the hood at Jalapeño's architecture, discuss the economics of AI, and wrap up with exactly how this impacts developers. All right, section 1. Let's meet the Jalapeño chip and see why we're entering a totally new era. Now, what really stands out right out of the gate is the timeline here. Just 9 months. I mean, think about that for a second. That is the incredibly rapid development cycle it took to go from their initial strategic partnership announcement with Broadcom in October 2025 all the way to a manufacturing tape-out and actually delivering physical engineering samples to OpenAI leadership. In the semiconductor world, a 9-month design-to-tape-out cycle is literally blisteringly fast. It pretty much tells us that OpenAI's model roadmap directly and urgently dictated these hardware specifications. Moving on to Section 2. Why build custom silicon? Let's talk strategy. Greg Brockman, OpenAI's president, actually framed the underlying philosophy behind this perfectly. He basically said they are building hardware precisely because they intimately know the software. They aren't just guessing what the chips need to do. Their own AI models literally assisted in the development process. They looked at the specific underserved computational workloads of their frontier models and realized that relying entirely on third-party general-purpose hardware was just leaving way too much potential on the table. It really boils down to a full-stack optimization strategy. OpenAI isn't just building a chip here, they're taking control of the entire vertical stack. By designing the infrastructure underneath their models, from the physical chip architecture and memory systems, all the way down to the networking topologies and request scheduling, they completely remove the abstraction overhead that typically bottlenecks throughput. When you operate across the entire stack, from the end user's product experience right down to the silicon itself, every single layer can be optimized around one unified goal, which is making the models faster, way more reliable, and significantly more affordable. Which brings us to Section 3, inference versus training, and finding the bottleneck. So to really understand why this chip exists, we have to talk about inference. Inference is simply the process of running those pre-built AI models to respond to your prompts and generate real-time tokens. The crucial thing to remember is that Jalapeño is an inference chip. It is absolutely not replacing NVIDIA's massive GPU clusters for the pre-training phase of these models. Instead, it sits downstream. Once a frontier model is actually deployed, Jalapeño steps in to handle that massive, relentless volume of user requests. You can kind of think of general-purpose GPUs like a Swiss Army knife. They are incredible because they can do almost anything, including that heavy-lifting training. But for inference, they actually waste a lot of precious compute cycles just moving data between high-bandwidth memory and compute units. And their PCI bottlenecks often end up fragmenting request routing. Jalapeño, on the other hand, is like a scalpel. It is custom inference silicon, laser-focused on the exact memory movement patterns and sequential KV cache-heavy nature of autoregressive decoding. It doesn't need to do everything, it just needs to serve tokens incredibly fast. And you know, the whole industry is recognizing this divide. Just look at how Google splits its 8th-generation hardware. You've got the TPU-8T, optimized specifically for pre-training, which scales to 9,600 chips in a single superpod for massive model building. But then you have the TPU-8i, built purely for inference, to break the memory wall by hosting massive KV caches entirely on silicon. Well, Jalapeño is OpenAI's direct answer in this exact same space. It explicitly bypasses those traditional GPU paradigms to optimize memory movement specifically for their frontier LLMs. The whole industry is dividing hardware based on the workload, and inference is finally getting its own dedicated silicon. Okay, Section 4. Let's take a look at Jalapeño under the hood and check out the architecture. So a big question you might be asking yourself right now is, how exactly do these specific architectural changes actually translate into measurable performance when we are serving these massive models? I mean, it's one thing to have a custom chip, but how does it actually move the needle on the metrics we care about? Well, the answer lies in their hardware ecosystem. Richard Ho's hardware team over at OpenAI took direct research feedback and handed it straight to Broadcom for the silicon design and manufacturing. Then Celestica stepped in for board assembly, rack-level integration, and high-performance networking deployment. Because the chip is built explicitly for the memory patterns of OpenAI's models, it heavily optimizes that KV cache-heavy decoding. And on top of that, Celestica's high-performance, rack-level networking simplifies deployment by entirely removing the need for custom PCIe bridging or those really complex software-defined routing layers. Next up, Section 5. Let's explore the economics of AI and scaling up. Broadcom's CEO, Hock Tan, dropped a huge detail here. He noted they are preparing for gigawatt-scale data center deployments alongside Microsoft and other infrastructure partners by 2026. Now, to put that into perspective, a gigawatt is roughly the power needed to run a medium-sized city. When you're operating at that scale, drastically reducing cooling requirements and power draw isn't just some nice technical feature, it's an absolute business necessity. So for all you platform teams out there, this creates some massive financial shifts. First, you get a lower cost per token, thanks to the reduced power consumption and higher throughput. Also, custom memory controllers specifically reduce the energy overhead that usually spikes during long context generation, when the system has to just repeatedly read that KV cache. You also get incredible latency stability because the request scheduling happens at the hardware level, which really cuts down on jitter across clusters. And early lab measurements, they show Jalapeño significantly outperforming current state-of-the-art general GPUs in performance per watt. Just think about what happens when you compound those performance per watt improvements across millions of concurrent user requests every single minute. It drastically and permanently changes the underlying economics of AI. And finally, Section 6, the impact on developers. What actually changes for you? First off, some really good news for the vast majority of you. You do not need to rewrite your inference code. If you're consuming standard APIs from OpenAI, absolutely no SDK changes are required. OpenAI is actively abstracting this new hardware layer behind their standard deployment stack, which means you get all the speed and cost benefits without having to change a single line of code. Now, on the flip side, if you're on an MLOps team building custom inference servers or hybrid setups, there are 3 structural adjustments you definitely need to prepare for once those public drivers are released. First up, serving architecture updates. Hardware-level scheduling might shift your optimal batch sizes, so you'll need to tune those batching strategies to maximize Jalapeño's memory bandwidth. Second, you'll need to revise your cost modeling. Pricing is likely going to shift away from compute hour billing toward more token-tiered or latency-optimized models, simply because the marginal costs are dropping so much. And third, review your deployment pipelines. You've got to evaluate how Celestica's standardized rack-level networking is going to affect your container orchestration. Obviously, wait for the public hardware specs before you start refactoring your kernels, but you should definitely start planning that roadmap right now. And honestly, the wildest part about this whole thing? This is not just some white paper pipe dream. These engineering samples are humming away in labs right now. They are literally executing real machine learning workloads today, including agent decoding models like GPT 5.3 Codex Spark. And they're running perfectly at their production target frequencies and power envelopes. The hardware is very real and it works. Which brings us to the end of our explainer today and leaves us with one pretty massive question to chew on. If a software company like OpenAI can now optimize the entire stack, from the very moment you type a prompt, all the way down through the memory systems to the physical silicon networking topology, what exactly does this mean for the future of traditional hardware vendors? It's a fascinating disruption for sure, and I am super eager to watch how this whole hardware revolution unfolds over the coming months. Thanks so much for joining me to explore this today, and I'll catch you on the next explainer.